this train.
Okay, so thank you for coming to this talk. And Alan and I are co-hosting the visitor, and Alan will do the actual introduction.
You are eating already.
So I'm happy to introduce today Dr. Shinnosuke Seki. He did his PhD at University of Western Ontario in London, Canada, and the title of his thesis was Combinatorial on DNA sequences. After that, he did a 1-year postdoc in Kyoto, and he is currently at Aalto University in Helsinki, Finland, where he recently received a prestigious Academy of Finland postdoctoral research grant for 3 years. So I had the pleasure of getting to go out and work with him in Helsinki for a couple weeks, which is actually the first time I met him, despite the fact that we've previously written a paper together to appear in Isaac 2013. So, and the name of the talk is Combinatorial Optimization in Tile Self-Assembly.
Okay.
So thank you very much for Professor Minakao and Eric for such a nice invitation and introduction. And thank you very much for all audiences to join my talk. Today it's very prestigious opportunities to introduce my work, but more importantly, I wanted to introduce this field called DNA self-assemblies to general audiences, and then tries to make more popularities of this topic. So today I will talk about this combinatorial optimization in self-assembly, but actually maybe combinatorial optimization part is just the last 15 minutes or so. It's a bit too technical, but more like our main purpose of this talk is to introduce this model of self-assembly and why people want us to talk about, why people want us to examine it. So like practical applications and motivations. So welcome. Okay, hopefully you can find welcomes in your own language in this picture. Oh, there are lots of ways to say welcomes. In Finnish, we say, what was that? Somewhere around. Tervetuloa. Thank you. Yes, tervetuloa. Yes, that's somewhere here. Okay. Yeah, here. Tervetuloa. Okay. So then question is, why do we have so many languages in this world? And then of course one explanation is due to our arrogance, got pissed off, and then he took our abilities to communicate with each other by one own language. But let's talk about some bit more scientific explanations. So another explanation is done by self-assembly. Okay, so what self-assembly of language? So according to some theories, maybe people start talking with each other, and then, of course, sometimes people change the communication topologies. Sometimes they go to the new continent, or then so they change their ways to talk, and through these communications, they figure out, oh, I should say this ways to make myself clear, so I shouldn't say that or that. But depending on the topology, some people can communicate with each other, but the other people cannot communicate with each other. Some people find, oh, this is a better ways to explain something, but some people find another ways to explain some things. And then yeah, we get many different languages like Finnish, English, etc., etc. But key point is that so nobody else is seeing us from outside of these worlds to say, oh, you have to understand this English grammar should be like this or that. Nobody can say such things to this communication. So key point is that just agents, in this case human beings, just communicate with each other, but actually there is no some external controls which controls the behavior. Okay? So this communication is very local. There is no global control. That's the key of self-assembly. But let's say more examples. So another example of self-assembly, it's a repeat bilayer. So our cell is surrounded by these repeat bilayers, but this repeat bilayer is also assembles autonomously. Okay, so this repeat has this very simple structure. Of course, I shouldn't say it's simple. It's a very complicated, but very simply, like we can say this part has a head and tail. Okay, this head is hydrophilic. This tail is hydrophobic. So just this tail doesn't like water. Okay, so if we put this repeat inside some water, in this case, they try to put their heads towards the water, and then they put their tails outside of the water, so opposite side of the water, then what we get is this. Okay? So this repeat bilayer self-assembles from very simple rules that you should not put your tails on water side. Okay? Just from these simple rules, we get such a very nice structure. And lots of another examples, like snow crystals, or pattern of zebras, or our galaxy, or our city, or our biggest enemy, okay, called virus. So let me summarize. So what's self-assembly? Self-assembly is a phenomenon in which something complex comes out from very simple local interactions among simple components. Okay, so these components do not have so many complicated functions. I don't say that human beings are not complicated, but it's just when we think about self-assemblies, we usually think about some very simple agent. And key is this: without external controls, or maybe with limited external control. All right. So, okay. So up to here is the basic notion of self-assembly. So is everything clear? Any questions? Whenever you have a question, please just raise your hands. I'm okay. My talk is just short, so it's a big help that you interrupt and then ask questions. All right. So then I'm a computer scientist, so I wanted to talk about some computational models of self-assembly or inspired by self-assembly. Actually, it's huge, so I cannot put whole list on this slide, but let me introduce a few. So tile assembly models, which is called TAM, introduced by Winfrey, 1998. Another recent hot topic is the chemical reaction network, or population protocols, or a very new one is this new bot models. This year, just a month ago, by Woods, other people, and etc. But I don't have enough time to talk all of them, so let me just talk about this tile assembly model today. But the other things are completely different, models inspired by self-assembly. So if you have interest, then I try to answer your questions as much as possible. So please ask me after this talk. So this tile assembly model by Winfrey is originally motivated by this engineering goal. So what we wanted to do is just very simple. We have DNA sequences put into test tube, and we get circuit. That's what we want to do, that's the ultimate goal. So first, I say molecular self-assembly, but actually what we use is usually DNA. So why we use DNA for self-assemblies? So it's according to Dotty's excellent summary last year. So it's DNA is a molecule of choice in many labs because very easy to synthesize. It doesn't mean that it is free. We have to pay monies to the companies. But anyway, if you have money and if you know how to arrange the sequences, then we can easily synthesize it. And also, its physical properties are very well understood. And also, it has properties to bear the information from generation to generation. Then we, of course, have another choice like RNA or proteins, but up to now, like a DNA is the most popular choice. But it doesn't mean we cannot use RNA. Like many applications use RNAs or proteins like for their own properties. But now let me talk just about DNAs. So then what we want to do is from DNAs, we design some DNAs which turns into circuit. So how to do? So first, what we make is from DNA, we make some interactive unit called interactive DNA tiles. Okay? So Winfrey and Liu, Venstra, and Siemens implemented this interactive DNA tiles in vitro, okay, in 1998 using these DNA double crossover molecules. So it is like this. So it consists of, say, 5 DNA sequences, I think. They have their own colors. So green one, red, purple, blue, and yellow. And they just get tangled together. Then key point is that this DNA is always searching for friends. Okay? Single-stranded DNA is very unstable. So that's why this red ribbons is always paired with this blue ribbons according to this specific rule called adenine should be with thymine and cytosine should be with guanines. So according to these rules, always this red ribbons is searching for the friends to bind together to make this spiral so that it is stable. Okay? Single-stranded DNA is quite unstable. So we use these properties that they're always searching for friends. So in this DNA crossover molecules, almost all parts are well paired. Okay, they already found their friends, so they're happy. But at the edge, here, actually there are 4 single-stranded DNAs. So they are unstable. They want us to be with somebody. Okay, but specific partner, not anybody, but some specific partner according to this rule. Okay? So what happens is that if we make these tiles a lot and then put into the test tubes, then these tiles, they just tries to bind together like this. So in this case, these red ones found another red ones, and then their hand shaked. So this part shaked, and then they get together. Okay. So using these properties, if once we put lots of different tile types, okay, depending on this single-stranded sequences or depending on this sequence, their way of binding is different. Okay, I don't say that any tiles can get together, but let's say, for example, like this one must shake hands with this one, or we can control such behaviors by designing these sequences properly. So then they bind, get together. Then what happens is that we get such a nice structure. So this is a AFM image. So what's going on here should be clear for the computer scientists. It's a binary counter. So starting from this this like gray things I'll explain later. So then if we design tiles properties, then what we get is they start counting. 1, 2, 3, 4, 5, blah, 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 blah. And according to this AFM image, it's actually ongoing even in vitro. So it's not just a series, but we can make such DNA tiles which count the numbers. Okay? And let me say one thing. So this black box or gray box is just an initiation part of this assembly system, assembly process. It's by DNA origami, one of the most important achievements in this field by Rodemund at Caltech in 2006. This allows use to force DNA sequences into any shape. I can say any shape you can make by folding these DNA sequences as we do origami. But here I cannot talk about it. So if you have an interest, then please ask me about DNA origami. But you can make anything. You can make USA flag, you can make smiley marks, whatever. Right. So let's shift a bit more computational science aspect. So Winfrey's this abstract tile assembly model is modeling the process of this DNA tiles assembly. So what we should do first is to abstract this DNA double crossover tiles, this with 4 sticky ends by square with 4 sides. Of course, square is 4 sides. And then each side has its own DNA sequences. So this corresponds to a single-stranded DNA sequence. This corresponds. So it has 4 sticky ends. And then sticky ends have its own sequences. So like ATT or CCG or ACT or some things. So it's just abstracted to be some letter, okay, like A or B or C. And also we have this function G which assigns each letters a strength. Strength is just a number like 0 or 1 or 2. So in these figures, this B doesn't have any strength to bind. This A has a strength 2, which is strong. This C has very like a weak strength. So the idea is that depending on the sequences of each sticky end, some sequences can bind very strongly. Okay, it's a very good for the stabilities, but some other group, for example, like this C, can interact with somebody but very weak. Okay, so it's not so good for the stability. But this is a key for interesting behavior. So let's see what happens in the examples. Yeah.
So what exactly is the sticky and what am I seeing 5 of them instead of 4?
5? No, it's just 4. So this like this like a gray box just shows how like the strengths. So this case is strength 2. 2 bonds. This is 1 bond. This is 0 bond. So each side has its own 1 sticky end. Okay, is it clear? Okay, so blah. But let's see example first. So this is just what we saw, this binary counter, and this tile assembly models. This system begins with a seed, some specific start tile. Okay, so this one. So this corresponds to this gray box. Okay. Let's see, starting from this, and I use these 7 tile types. Okay, each has its own strengths and this letter. Okay, so now we have this seed with north and east of very strong glue. So for example, this tile can attach here because it has N to the south and it can match with this N, and also strength is enough, so they can attach here, here, like this. We get this L shape. Clear? Okay. And then interesting thing happens here. So at this point, let's see this position. This position has a support from the west and from the south, but both supports are quite weak. But they cooperatively bind these orange tiles here. Is it clear? 1 + 1 = 2. So now, without this south support, it's too weak. So it cannot bind, but with both sides support, now this can stay there very stably, very comfortably. It can stay there. Is it clear? Yep.
Is it possible to rotate the last tile?
Rotation prohibited. Okay, rotation is prohibited. But of course, we have new models in which rotation is okay. So in this original model, you are not allowed to do this. But inside the test tube, of course, that's more natural, that they just change their orientations. But in this model, don't rotate, okay? So then just continue.
Sorry.
Yeah.
But the strength of the south side is like it's 0. So
Sorry, this 0 is label. This is a letter.
Oh,
I'm so sorry.
Okay.
I'm so sorry. Yeah. So for the strength, please count this.
Okay.
This one. Then we get binary counter. Yeah.
So there's a rule that only labels, the same label has to...
Yes, yes. Because each sticky end has its own specific, like, sequence, like ATT. So ATT can bind only with TAA. Okay? So if sticky end is different, in this case, no matter how strong they can be, they are just, oh, you are not my partner. Okay? All right, another example is square. We want to make another square. So let's start from seed. In this case, what we can put is just this one, because now we have only one choice here to the east. So we have this, okay? And here we have double bonds, so we can get this, something like this. Then we can make square, okay? Then key point is that this system does not make anything but 4 times 4 square, okay? So the target is very clear, 4 times 4 square or nothing else happens. So such kind of like a programmability is very important when we actually work on experiments, because error is just a waste of money for the laboratory people. Okay? So using these same ideas, we can easily see that not only for n equal 4, but for any arbitrary n, if we have n plus 3 different tile types, then we can make tile systems which assembles this n times n square. Okay, just extend these ideas. So instead of this 4 hard-coded part, we can make n hard-coded part, and then start letting the second rightmost ones to have these double bonds, and then what happened is kind of like a stair back to this ways, and then just this green one just fills this part by its own. All right. So this I already mentioned the notions, but directed TAS, this is just a TAS which is guaranteed to make specific type, specific shape or patterns or something, but doesn't make anything else. That is a definition of directed ones. The motivation is that just errors or undesirable patterns is just a waste of money. Okay, that's a very practical motivation. So we just talk about these directed systems in this talk. Okay, so what's research goals in this field? Lots, okay, but just some. So of course, this is a basic motivation. We wanted to make shapes or patterns self-assemble. We don't want to control from outside, but we just encode these DNA tiles and put into the test tubes, then they just automatically come out. So that is practical motivation. And as a computer scientist, we are wondering what can we compute by this system. I will talk about later. And another question is, this is the motivations for my talk. So how concisely can we design a TAS? What does this mean, concisely? Concisely means that how many different DNA tiles we need to design. So design means we need to figure out what the sequences of this DNA so that we do not make something like completely nonsense. So for each DNA tile types, we need to encode or we need to design these sequences, but this sequence design is a very difficult task even using computers. So if somebody says that, oh, I have a system with 100 different DNA tile types which makes square, versus somebody say, oh, you're nonsense, I need only 7 tile types which makes the same things, then of course you should choose the latter one, because we need to just design 7 different tile types instead of 100. So that is a motivation for optimization in this research program. And of course, I'm talking that, oh, the self-assembly behaves very well, so it doesn't make any errors, but of course it does. So they do not follow our rules so easily. They always try to bind. Even illegal bond often happens. For example, I said, oh, ATT should be with TAA, but sometimes they get ATT with TCA, still maybe like make this kind of like a bond. So the second one doesn't match, but still they can make some illegal bindings. So then I wanted to make a binary counter, but they just doesn't count something but make smiley mark, or it can happen. So how to find such a error-prone or fault-tolerant systems, that error correction. And of course, we wanted to do in vitro implementation, etc. But let me just talk about the computational powers and optimization today. Okay. Any question up to here? Okay. So first, I wanted to talk about computational power of tile assembly systems. What it can do is this. So in his PhD thesis, he proves that tile assembly system is Turing universal. So this means you can compute by these systems whatever computable. Okay? Or in computer science terminologies, it's equivalent to Turing machine for computational power at temperature 2. Okay? Sorry, I didn't mention any temperature, but temperature means that how strong the glue has to be for the binding. So temperature 2 means that you need 2 double bonds or 2 single bonds for the bindings. Okay? So if temperature is 1, in this case you don't need any double bond, because temperature 1 means whenever you find even like a weak bond, it's enough because temperature is very low. Usually DNA has these melting temperatures at which they start get off, okay, get separated. So if temperature is low, then even with very like a weak bond, they are still comfortable. But if it goes up to 90 Celsius, or then they start getting off, so they need more strong bonds for the stability. Okay. So if you can use such kind of like a cooperative bindings by weak one and weak one, then this is Turing universal. But question is the following. So temperature 2, this means that you need strong binding and weak binding. This kind of like a different energy levels makes the implementation way harder. So if you do not have to use 2 different strengths, then experimental people are quite happy. So conjecture is this. If tile assembly system is at temperature 1, is it still Turing universal or not? That's one of the most important open problem. People want us to know, nobody figure out. So if people want us to try, then please try. Everybody wants to know this conjecture, but very likely it's not. So this is a conjecture by Doty, Patitz, and Summers 2 years ago. So they think that this tile assembly system at temperature 1 is as computationally strong as semilinear sets. So semilinear set, I need some explanations, but semilinear set is kind of like a set which can be computed by just counting. So, but now I don't have time to explain, but it's much, much weaker things in which many problems is decidable. Okay, so it's very likely it's different from Turing machine, because for Turing machine, almost everything is undecidable. Then, one interesting result about this conjecture is the following. So instead of thinking about 2-dimensional tile assembly systems, people also think about three-dimensional tile assembly system in which we consider not the tile but cube. Okay, cube get together and piled up like Legos. And in this case, temperature 1 system is already Turing universal. Okay, so that's a very interesting result. So this means that to prove this conjecture, we need to use some planarity. Why do we have to stay on the plane to prove that this is impossible at temperature 1? But maybe it's possible that temperature 1 system is as strong as temperature 2. That's more surprising. Yeah.
Can you clarify what exactly TAS as a computer is? So what is the input, what is the output?
Okay. That's a good question. So let's say, for example, like Turing input can be considered in a many different ways. But for example, tile assembly system has different tile types, right? Type A, type B, type C, or some things. So imagine that you are just given some like a ribbon of some A, B, C, A, B, B, or something. This is kind of like an input. And then you make some kind of like a space-time diagrams. So it just, we simulate some Turing machine's behavior. So this is kind of like a concept to be Turing machine tape. And then one step, one step, one step, blah, 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 blah. Then maybe it doesn't stop, we don't know. But when it stops, then we just read the final configuration. Okay, this is the output. This is one way.
So then, is there ambiguity? So when you have a new file on the tape, so if there are multiple places it combines, so
yes, so for Turing machine simulation, we need to prevent, such kind of like opportunities, because in the Turing universal simulations, what it happens is just at some specific point where Turing machine puts its state or its head to be double bond, and the others are all single bond, and then at this point, some like a final state control tile comes here, then do some head simulation around a bit, and then just copy of the other part, and then go up, up, up. So that's one very, how to say, naive simulations of Turing machine. So that's one way, but of course we have many ways to interpret what is this tile assembly systems computes or some things. So another idea is that if, like, for example, like we can consider, let's say, so maybe this is not a good example. So let me talk about it later. But at least is it clear that we can simulate Turing machine by tile assembly system? All right. So then I don't have so much time left. So let me talk a bit about combinatorial optimizations. Okay. So tile complexity. Tile complexity is the motivation of our programs. So question is how to evaluate the conciseness of tile assembly system design. So I already gave one example that you have some goal, and then two guys say, oh, I can achieve these goals using 100 tile types. Then the other person says, oh, no, I can do that by 7 tile types. Then in this case, this guy's tile assembly system is simpler, okay, because we need to have only 7 tile types. So that's tile complexity, okay? You are given some things, somebody said, please make smiley mark. And then, oh, I can make it by 8 tile types, or oh, I can make it 6 tile types, blah, blah, blah. So tile complexity is the minimum number of tile types we need to achieve the goal. How many different glues we need, how many binding strengths we need, temperature. And also we can think about time analysis, how fast this target can self-assemble. But I cannot talk everything, so just let me talk about tile complexity today. I already talked the motivation. It's related to money, okay? We don't want to pay lots of money to the DNA synthesizing company. All right, so tile complexity definition is blah, 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 blah. Okay, so this is a definition for the shape self-assembly. So you are given some shape. Shape, it just says you are given some XY plane. and then to 0, 1. 0, 1, 0 means not full, not filled, 1 is filled. And then the blah, 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 tile complexity of this shape is minimum integer n such that directed temperature to tile assembly systems assembles S using this number of tile types. Okay. So, for example, binary counter tile complexity is at most 7 because there is this specific systems which makes this binary counter. Is it okay? For square, this is at most n plus 3 using this ladder construction. Okay, but I said at most because at most means at least I have this example, but maybe somebody's come up with very nice constructions to make this using 6 tile types. It may be possible. And also this is at most, but I don't say this is the best because there is a result by Edelmans and other people, 2001. They said this tile assembly, this tile complexity is this, order log n over log n. And for any algorithmically random number n, this is tight. We cannot go down. Because if we could go down, this is contradictory to Kolmogorov complexity. But we can prove such kind of like a nice result. Okay. Then question is, this experimental people says, oh, I want to make this. Please compute the tile complexity. How simply can we make tile assembly systems? So that's very practical problems. But this kind of problem is usually difficult, but sometimes positive results can be obtained. So by Edelman's other peoples, they showed the polynomial time algorithms for computing the tile complexity of square. Okay, square is quite important shapes for in the practice. So it's a very nice algorithms. And this S is me, but we actually extended these algorithms for arbitrary temperatures. So even at any temperatures, not only 2, we can compute this tile complexity in polynomial time. But usually we do not have big hope because of the existence of these NP hardness problems. So they proved in the same papers that for arbitrary shape, we do not have such a hope to design polynomial time algorithms because it's NP hard. So unless P equal n P, we do not have any hope to compute this for given shape in polynomial time. Okay. So tile complexity is computable, but sometimes or often cases that it's quite difficult to compute. So I was talking about shapes, but I want us to talk about some pattern assemblies to conclude my talk. So pattern assembly is a bit different from shape assemblies. So pattern assembly is the following. So what's a patterns? So pattern is some functions which assigns for each positions a color. Okay. So in this case, this is the patterns. The first row is gray, and these two parts are red, and these 3 positions are blues, and the others are green. So this is the pattern. And then why do we have to think about pattern assembly? So pattern assembly is motivated by the implementing some circuits on DNA assemblies. So first we make some kind of like a frame, but on which we implement actually some computational units. For example, like transistors or wires or some. Of course, it's some biological counterpart of these computational circuits. But actually now we can put for example, wires. It's also DNA sequences, but on this DNA like a tile or plate, so that you can send some signals from one part to another part. Or you can implement, for example, like an AND gate or OR gate or NAND gate or XORs on this plate so that actually you can compute anything, because and ors, then yeah, you can make many like circuits. So question is, so actually at each positions, for example, if on this or on this, you can put, for example, AND gate or OR gate. So let's say this green is like a wire, this blue is AND gate, or this red is OR gate. Or then question is, on each tile type, you have some specific computational unit. And question is, can we design some tile assembly systems which assembles into some specific circuit patterns? Okay, so it's okay to put AND gate on different DNA tile types. So it's okay to have many different blue tile types or many different red tile types. But target is each color corresponds to some specific functionalities. And then question is, can we make some tile assembly systems which aligns into some specific pattern so that the resulting pattern or resulting self-assembled these things works as a circuit for some specific circuit design. So that is the motivation of pattern assembly. And so then in this pattern self-assemblies, we use some specific simple rectilinear, simple tile assembly systems called rectilinear systems, which works in this way. So it starts rather with some specific L-shaped seed, and all strength is 1. Then so always tiles needs cooperativities because it's temperature 2. So from this seed, this assemblies proceed in this ways, from the left bottoms to the right top. Okay. The reason why we think about such simple tile assembly system is because it's easy to implement. Because it has just only strength 1 group, so it's very easy because we don't need to implement this and this different powers. All right. So we just consider this very simple tile assembly systems. Then we ask the same question. So we are given a pattern. Then we wanted to know the smallest, simplest tile assembly systems, rectilinear ones, which makes this pattern. Okay, this is the tile complexity problem. Then this problem is NP hard. Ooh, that's very discouraging, but it's NP hard, unfortunately. But key point is that this pattern doesn't say anything about how many colors it includes. Okay, but our motivation is circuit design. Can we imagine some circuit which contains 100 different components on it? It's very nonsense. We just need AND gate, OR gate, wire, something, then we can make whatever we want. So question is, if pattern is guaranteed to contain some limited number, let's say k, then is this still NP hard, or can we compute the minimum tile complexities? That was the questions. And then I proved that it's NP hard for 60 colors. Okay, it's a polynomial time reductions. But people say 60, oh, it's nonsense. It's so too much. Do you consider 60 different components on the circuit? Okay, our answer is 29 is NP hard. It's Professor Kao and Arek. We proved this and recently accepted to Isaac. Then, good thing is this next theorems. Next theorem says that even the approximation is tough. Okay, tile complexity is a minimum, but even so small is good for application. But we destroyed this hope by proving that even approximations with the ratios 47/46, it's NP hard.
But that's supposed to be higher than 29. Not
Yes,
lower, right?
for 29 or more.
Right. So
case.
for lower, there is still hope.
Yeah, so for less, still we have a hope. Conjecture is this: 2 parts is NP hard. You mean even 2-color case, this is NP hard. That's conjecture. Okay. And news is recently we had a conference DNA in Arizona. Then these people figure out some promising approach to this 4-color pattern assembly NP hardness. So we are not so far anymore from the conjecture we hope, but still it's just some promising approach. So if you are interested in, then I can talk about some ideas later. Okay, so future works is, of course, this solving conjecture, but more important thing is approximation algorithms. Okay, so we do not have a hope with under the ratio of 47 under 46, but maybe 2. Approximation ratio 2 is still possible, and it's very nice for the, our experimental implementation. So this is actually what we wanted to do. So now I conclude my talk, but of course I talked about DNA pattern assembly a lot because I'm working on, but I also want us to introduce other people's hot topics. So for example, one is for this one, intrinsic universality. So intrinsic universality is the following. So can you design some one single tile assembly systems which mimic the behavior of any other tile assembly systems? So behavior doesn't mean that the result is the same, but also this process of assembling can we simulate by only one universal machine. Then actually it's possible. It's a very surprising result by Dave Dotis and other peoples. And another one is called the signal passing tiles. So this signal passing tile has almost like wires on it. So it receives some signal from one side and it can translate this signal to the another side. So this tile itself works more as a computational unit rather than just a building block. In the current tile assembly system, once they get attached, then they don't do anything anymore. But in the signal passing tiles, they can send the signals on it, or even they can activate some other signals, some deactivate some signals. So sometimes tile fall apart, or such kind of things can happen. And now this is very new topic, but nice papers just come out. So we have a very promising, we have very big expectations on the signal passing tiles. So, and further reading, hopefully I could introduce the basic ideas of these self-assemblies. And then you can find a very nice surveys in the computation of the ACMs last year's called Theory of Algorithmic Self-Assemblies by my friend David Dotis. So this is a very good summaries of from theories to the implementation, the experiments. So I strongly recommend you to read these papers if you have interest in this topic. So thank you very much for your attention and cordial invitation. And thank you very much for Academy of Finland. Thanks.
Any questions? Okay. For the original circuit problem, what's how many colors you need in
That's a good question. So what kind of circuit do you want us to make, right? So for example, if we have AND or not, then we can make any kind of a circuit. So in this case, maybe 3 colors and or not plus wire, say 4 colors or some things. But of course, 60 is too much. Even a 29 is still too much. So that's the motivations. We want to decrease the colors up to 2, if possible. Yes?
Talk about files that can transmit signals.
Yes.
So, what kind of technology how fast is
That's a good question. So, last year, I talked with Natasha Jonoska, a professor at South Florida University, and she said that now at most 5 tiles they can signal, then stop.
Right,
experiments. Okay.
It's like biological.
Yeah. Yes, it's a biological signals. So actually, on these tiles, there is some DNA sticking out, and then it's just like so there is some kind of like a hairpin structures on some tiles, and the hairpin structure is stable because it's already found the friend. But actually, so on this DNA tile, there is another guy who is looking for its partner, and it comes like this, and branch migrations, it flipped off. Then this signals is now activate, and of course it can come back here and then putting back because this is just a random walk. But using clever DNA sequence design, we can make kind of like a, how to say, direction. So it comes out, but instead of going back, this guy tries to find another partner somewhere.
Structural
Yeah.
kind of signal. Right?
Yes. Yes. But using this direction, like directionalities, we can make some kind of like a domino effect. But due to the current up to the up now today's our technology is not so advanced enough. So after 5 dominoes, it stops. But that's matter of technology. So definitely we can advance very quickly. But due to the reasons, it's better to think about some signal propagation distance. That's what we are also thinking, like on this theory, like how far we need to propagate the signals. If we do not have to do that so much, then that's nice. Current technology is enough to implement that. But if we have some let's say Turing machine simulations which needs to propagate from one side to the opposite side of the tape, that's nightmare because we don't know how far we need to make this Turing tape. So yeah, but there is actually the implementation paper came out this year from this DNA by Natasha Jonoska and other people. So it's now available online. So you can read how to implement this domino effect and with experimental results. So it seems promising.
Any other questions?
So you talked about DNA origami.
Yes.
And a lot of the things you showed were just on these rectangular,
right.
Rectangular shapes.
Yes.
Can you use the same type of implementation to predict the shape of an arbitrary shape, not just a rectangular shape?
Yeah. Yes, we can. Yes. But for this DNA origami is just so DNA origami's idea is you have very long single strand sequence. Okay, and also we make some kind of a very short stapler. Okay, so what you do is to fold this long sequence like this and staple it, and for some parts and then staple it, Then we make some specific shapes. We can do any kind of shapes, but it's a bit different from self-assembly. So you are given some a specific a target, and then you design some specific staples so that it falls into. But so this is different from different kind of self-assembly. So just single strand, like a folding of single strand into some shapes. Then this is a bit different. So we have some computational a reaction unit, and then they get together. So it's a self-assembly of different tastes. But from this tile assembly system, also you can make any kind of a shape, but of course it's quite difficult to design such a nice systems because, as I said, tile complexity computation is NP hard. So I'm sorry, maybe I didn't answer your questions properly, but so any kind of arbitrary shape we can make from this both things. But for depending on the applications, people use origamis or people use tile set systems or something else. So it's very application dependent issue.
Any other questions? questions? And thanks, speak again. Thank you.